Good morning, students. Let us continue 11th chapter. Last video we discussed about heating curve of ice. There we discussed an experiment where ice at 0 degrees Celsius is heated till it becomes water at 100 degrees Celsius. And we could see in that experiment heat absorption takes place in two steps. In the beginning, heat is utilized for changing the state, means ice at 0 degrees Celsius changes to water at 0 degrees Celsius, means change of state happens. When change of state happens, temperature doesn't change. In second stage of the experiment, temperature changes. That means water at 0 degrees Celsius changes to water at 100 degrees Celsius. And its heating curve also we discussed in the last video. Now one more experiment, heating curve for naphthalene. Naphthalene is a solid almost like wax, and we are going to make the heating curve for naphthalene. So here the experiment goes like this. We have taken some naphthalene, powdered solid naphthalene at 30 degrees Celsius, and we are going to heat it continuously till it changes into liquid at 100 degrees Celsius. In the beginning, and we have to note down the temperature and time at regular intervals. So in the beginning time, thermometer reading is 30 degrees Celsius, and we start heating. So beginning we have solid naphthalene at 30 degrees Celsius. As the heating process starts, the thermometer reading will be going on increasing. It slowly goes on rising and it reaches up to 80 degrees Celsius. Solid wax at 30 degrees Celsius, its temperature rises and reaches up to 80 degrees Celsius. Suppose the time taken for that is 10 minutes. So during this 10 minutes time, temperature of naphthalene goes on rising. State is not changing. This naphthalene remains in the solid state, but the temperature goes on rising. So for that purpose, means for temperature change, heat is utilized for this 10 minutes time. So here we noticed the temperature, the reading on the thermometer was slowly going on rising from 30 in where it reached up to 80. Now once the temperature reaches 80 degree, it remained steady for some time. For next 5 minutes time, suppose next 5 minutes time, the reading is not changing. It remains at 80. That means during that 5 minutes time, temperature is not changing. Reading on thermometer remains as 80. Here the reading mercury level remains steady. That means during that time the heat supplied is utilized for changing the state. That means the solid naphthalene now changes into liquid naphthalene. So in the second stage of the experiment, temperature remains constant, means state is changing. So total 15 minutes heating process is over now. So that means at the end of 15th minute in the vessel there will be liquid naphthalene at 80 degrees Celsius. Suppose we continue the heating for next 5 minutes, next 5 more minutes. Then you will see after 15th minute, that means the whole naphthalene got melted at the end of 15th minute, 10 plus 5. So from 15th minute onwards, from 16th minute onwards, mercury level in the thermometer will start rising upward. Suppose at the end of this total 20th minute, there is liquid naphthalene at 100 degrees Celsius. So we stop the heating process here. Total 20 minutes we were supplying the heat, and this was the change happening. So once again you can analyze the experiment. First 10 minutes temperature changes, state doesn't change. Next 5 minutes, temperature doesn't change but state changes. Next 5 minutes, temperature changes and state doesn't change. And we are going to plot this observation on a graph. That graph we call as heating curve for the solid naphthalene. Here temperature and time. Time we are plotting on x-axis, temperature on y-axis. Time in minutes is plotted on x-axis and temperature in degrees Celsius is plotted on y-axis. On y-axis I have plotted only the required values. 30, 80, 100. These are the temperature readings we require. So only that readings I have plotted. So let us start from the first stage of the experiment. First 10 minutes time. This is 10 minutes time. The temperature changes from 30 to 80. Starting time, temperature is 30. So here is the starting point of the graph. From 30 it starts. It reaches to 80 at the end of 10th minute. So when the experiment starts, that means time 0, temperature is 30 degrees Celsius, and by the time when by 10 minutes time the temperature changes from 30 to 80. It reached to 80. So here is the second point B. So AB is the graph line for this section. Now next 5 minutes temperature is not changing. Next 5 minutes means 10th minute to 15th minute. Temperature is not changing. Then next 5 minutes temperature changes from 80 to 100. So you got the heating curve as A, B, C, D. So at the point A, you have solid naphthalene at 30 degrees Celsius. At B, what is there in the vessel or what is the substance in the vessel? That is liquid naphthalene at 80 degrees Celsius. At this point in the vessel, there is, here solid naphthalene. In the beginning of the graph means at the point A, you have solid naphthalene at 30 degree in the vessel. At the point B, that 30 degree temperature rises to 80. So during the section AB, temperature was rising from 30 to 80. Then for next 5 minutes temperature doesn't change. So what is happening during this section BC is melting happens or fusion happens. That means solid naphthalene at 80 degrees Celsius changes to liquid naphthalene at 80 degrees Celsius. So melting process happens during this section BC. During the section AB, temperature rises. During the section BC, melting or fusion happens. Again, what is happening during the section CD is liquid naphthalene at 80 degrees Celsius changes to liquid naphthalene at 100 degrees Celsius. So here temperature changes, here state changes, here temperature changes. Finally, at the end of 20th minute, 10 plus 5 plus 5, 20th minute, in the vessel there is liquid naphthalene at 100 degrees Celsius. So this is the heating curve. From the heating curve, you can find out what is the melting point of naphthalene. Solid naphthalene can change into liquid only at a fixed temperature of 80 degrees Celsius. So that temperature we call as the melting point of solid. Melting point of naphthalene is 80 degrees Celsius. Now you can make the cooling curve. We are going to see the reverse experiment. means liquid naphthalene. We finally at the end of this 20th minute there is liquid naphthalene in the vessel at 100 degrees Celsius. That liquid naphthalene we are going to cool. There also temperature and time values you have to record. So initially there will be liquid naphthalene at 100 degrees Celsius in this vessel. Reading will be 100. Then we are allowing it to cool. Cooling means heat will be liberated. So you will observe the experiment or mercury level in the thermometer coming down. In the beginning reading was 100. Here the substance was in liquid form, and in the first few minutes time temperature will be falling. Once it reaches 80 degree, it will remain steady for some time. During that time, liquid naphthalene is again changing to solid naphthalene, means freezing takes place. Then again after some time, the temperature will be coming down up to room temperature of 30 degrees Celsius. So how will you plot the cooling curve? Here again, time you have to plot on x-axis, temperature on y-axis. So graph line starts from 100. Beginning time temperature is 100. Then it comes down up to 80. Then it remains steady for some time. Then it comes down to 30. So here the graph line is A, B, C, D. Heating curve goes upward. Cooling curve comes downward. So here we can analyze the graph in this way. During the section AB, here we have liquid naphthalene at 100 degrees Celsius. It changes to liquid naphthalene at 80 degrees Celsius during the section AB. During the section BC, liquid naphthalene at 80 degrees Celsius changes to solid naphthalene at 80 degrees Celsius. Liquid changes to solid means freezing takes place. Then during the section CD, this is C, this point is C, CD, solid naphthalene at 80 degree changes to solid naphthalene at 30 degrees Celsius. So this is the cooling curve. From the cooling curve you can find out what is the freezing point of naphthalene. Liquid naphthalene changes to solid naphthalene at a fixed temperature of 80 degrees Celsius. That temperature we call as the freezing point. So you can see the solid naphthalene changes to liquid naphthalene, means melting happens at 80 degrees Celsius, and reverse. Liquid naphthalene changes to solid naphthalene at same temperature 80 degrees Celsius, but melting happens on absorption of heat. Solid naphthalene at 80 degrees Celsius, on absorbing heat it changes to liquid naphthalene at 80 degrees Celsius. So here heat absorption takes place. In this case, liquid naphthalene at 80 degrees Celsius changes to solid naphthalene, means freezing happens on liberation of heat by giving out heat. So the conclusion is this: the numerical value of melting point and freezing point are same. Another example, ice can change into water only at a temperature of 0 degrees Celsius. And reverse, water can change into ice only at a steady temperature of 0 degrees Celsius. So the melting point of ice and freezing point of water are same, 0 degrees Celsius. But melting happens on absorption of heat, freezing happens on liberation of heat. So numerical value of melting point and freezing point are same. Next topic, latent heat. In previous video I mentioned the word latent heat. Here during this process, during these last 3 experiments, the heat supplied was utilized for either changing the state or changing the temperature. The heat utilized for changing the state from solid to liquid is known as latent heat of fusion. When a substance changes from solid form to liquid form, during that time the potential energy of the molecules have to be changed. During the change of state, kinetic energy of the molecules are not changing. That is why temperature remains constant. But potential energy of the molecules have to be changed. You know, the molecular arrangement or configuration is different in solid and liquid. So molecular distance or molecules, their arrangement is to be changed. For that, heat is required. Means potential energy of the molecules are changing when they change the state. Kinetic energy is not changing, thereby temperature remains constant. But heat is required for changing the molecular arrangement. That is why in the previous experiments we could see that during the change of state, temperature is not changing. During that time, the heat supplied is utilized for changing the configuration of molecules. That heat required for the melting phenomenon is known as latent heat of fusion. The latent heat of fusion, it's per kilogram per unit mass. If you calculate the specific latent heat of fusion, that is known as specific latent heat of fusion. Like heat capacity and specific capacity, here also latent heat of fusion, specific latent heat of fusion is there. So definition goes like this: the amount of heat energy required for a solid to change into liquid without any change in temperature is known as latent heat of fusion, and amount of heat energy required for 1 kilogram solid to change into liquid without any temperature, that is known as specific latent heat of fusion. And for that, symbol is L. And the formula to find out specific latent heat of fusion is quantity of heat required upon mass of substance. Specific latent heat of fusion, L is equal to Q. Q stands for quantity of heat upon M, mass of substance. So here, based on this latent heat of fusion, you don't have any numericals. In textbook it is given, but it is removed from the revised syllabus. So in previous year questions, you will see so many numericals where the melting of ice is mentioned. That numericals you can avoid. Okay, you need not try that numerical. Wherever this melting of ice is mentioned. Okay, so this is the formula to find out specific latent heat of fusion. Q upon M, its unit is joule per kilogram. Heat is measured in joule, mass in kilogram. So joule per kilogram is a unit of specific latent heat of fusion. For ice, the specific latent heat of fusion is 336 joule per gram. It means that for 1 gram ice, 336 joules of heat is needed for melting. 1 gram ice will change into 1 gram water by absorbing 336 joules of heat. 1 gram water at 1 gram ice at 0 degrees Celsius will change into 1 gram water at 0 degrees Celsius on absorption of 336 joules of heat, or you can tell the reverse also. 1 gram water at 0 degrees Celsius changes into 1 gram ice by liberating or by giving out 336 joules of heat. So and it's this is in CGS system. In SI system, its value is 336 into 10 to the power 3 joule per kilogram. That means for 1 kilogram ice, 336 into 10 to the power 3 joules of heat is needed for melting process. Just for melting phenomenon, for 1 kilogram ice, 336 into 10 to the power 3 joules of heat is required. This heat or specific latent heat of fusion of ice is a very big value, and we can experience some natural consequences of this high specific latent heat of fusion of ice. Now let us discuss some natural consequences of high specific latent heat of fusion of ice. The snow on the mountains does not melt all on a sudden. In geography, you might have studied the names of rivers starting from snow-covered mountains. In these rivers, there is no flood happens in summer season. If you think there is chance for flood because ice will melt in large quantity on mountains in summer season and floods can happen, but it doesn't happen because of high specific latent heat of fusion of ice. For the melting of 1 kilogram ice, a large amount of heat, that is 336 into 10 to the power 3 joules of heat is needed just for the melting of 1 kilogram ice. Since it is a large number, the melting of ice is a slow process. Thereby the snow on the mountains does not melt all on a sudden. Same way, when 1 kilogram water freezes, 336 into 10 to the power 3 joules of heat is to be removed from water. Thereby freezing of water also is a slow process. Melting of ice as well as freezing of water is a slow process because of the same reason, high specific latent heat of fusion of ice. Thereby the water bodies like lakes, ponds and all do not freeze in cold countries. They do not freeze all on a sudden. Another example, the time just after the hailstorm, the temperature will be very low. During the hailstorm means the snowfall. During the time of snowfall or the time before snowfall, temperature will not be very low. But after the snowfall, the temperature will become very low. Let us see the reason behind it. Once the snow has fallen, it starts melting. And we have seen that for the melting of ice, large amount of heat is required. That heat will be extracted from the atmosphere during the melting of snow. Thereby atmospheric temperature falls to a very low value when the hailstorm snow starts melting. Another example, uh, do you know which gives more cooling effect? Water at 0 degree or ice at 0 degree? To cool down the soft drinks, we add ice at 0 degree. We prefer ice at 0 degree than water at 0 degree. Why ice at 0 degree can give more cooling effect than water at 0 degree Celsius? It is due to high specific latent heat of fusion of ice. Each 1 gram ice extracts 336 joules of heat from the drink just for the melting phenomenon. So the drink will get more cooling effect if we add ice at 0 degree Celsius. So these are some natural consequences of high specific latent heat of fusion of ice. With this, the chapter calorimetry gets over, and there are some topics in your book which are removed from the syllabus. Page number 249, change in the volume. What comes below that title, it is removed from the syllabus. Next page, again change in volume in boiling, that part is also removed. Then page number 252, consequences of high specific latent heat of steam and measurement of specific latent heat of ice. Measurement of specific latent heat of ice, that experiment is there, but consequences of high specific latent heat of steam It is removed from the syllabus. And this experiment, last part, how to find out specific latent heat of ice, we will discuss briefly. This experiment will not come in the exam. For the numerical purpose it is given. Since numericals are not there, you need not give much importance to the experiment. Still I will explain briefly. The experiment goes like this. You have to take a calorimeter, find its mass. Suppose it is M1. Half of the calorimeter is to be filled with ordinary tap water, and find out the mass of calorimeter and water together. Let it be M2. Then record the temperature of this water, initial temperature, let it be T1. Now add some ice cubes at 0 degrees Celsius into this water. Then the reading on the thermometer will be falling, because ice will extract heat from this water and vessel for melting as well as for increasing the temperature of that water after melting. So you have to go on stirring the solution till the whole ice gets melted and reaches to a final temperature of T2. Suppose T1 was the initial temperature, and after the melting of ice the steady temperature reached is T2. Now the whole ice got melted. Find out the weight once again. Let it be M3. So in this case, the bodies involved in the heat transaction are calorimeter, then water and ice. Out of these three, ice will be gaining heat, water and calorimeter are losing heat. Then you can apply the principle of calorimetry. Heat lost by calorimeter plus heat lost by water is equal to heat gained by ice. In that way, you can find out the specific latent heat of fusion of ice. Actually, it is removed from your syllabus, so you need not give importance to this topic. Okay, so the chapter is over now. Try to do the exercise questions and numericals. Numericals where melting of ice mentioned, you can avoid. Okay, thank you.